Alright guys, I'm going to show you a little bit about derivatives today. So derivatives are really interesting. Basically the idea behind it is we're finding the instantaneous rate of change of a function. We're basically just the slope of a function at one particular point in time. So I'm sure we're all very familiar with the idea of slope and how we find that. So if we look at the normal old linear function, we'll say y equals x. This is real easy because I can call this, let's say I'll call this 1, I'll call this 1, and I'll say, okay, well, the slope, it went up 1, right? So we have 1 over 1, so my slope is 1. That's pretty simple. And it's always going to be that same slope. But what if I have something with a changing slope, something that is non-linear, and I want to know its rate of change? So something like x squared, right? Well, I can't really apply that same principle as before. I can't go, so if this is x squared, and let's say I'm going to take 2, x equals 2, which will give us y equals 4. Let's say x equals 3, which will give us y equals 9. So I can't really do that same thing. So if let's say I take the slope between 2, 4 and the origin. So the slope formula, if you remember, is y2 minus y1 over x2 minus x1. And I'm taking it from 2, 4 to 0, 0. Or the other way, rather. So my x2 is going to be 4. I'm sorry, my y2 is going to be 4. My y1 is 0. My x2 is 2. My x1 is 0. So the slope right here is 4 over 2, which is 2. But what if I do this? What if I go, okay, well, let's find the slope between 2 and 3. So I have, let me do it on this side. I have 3, 9, and 2, 4. Same thing, so y2 minus y1, 9 minus 4, over 3 minus 2. Well, now I have a slope of 5. So our slope is constantly changing. So what we do is we take that simple slope formula, and what we want to do is we want to make the difference between the delta x, the change in x, infinitely small. So that's the idea here. So we're finding the slope as these 2 points get closer and closer and closer, and infinitely close is the idea, which will require limits. So let's rewrite this way. I'm going to have to write this equation a couple different ways. So delta y, delta y over delta x. So that's pretty simple. That's just another way to express that slope formula. So what if I do this? What if I call this, get rid of all this. What if I call this what was 2, x, some point of x, and then this some new point of x, which is just x plus h. X plus some difference, right? So that makes this right here h, right? If this is x, and this is x plus h, then the difference between them must be h. So why is that helpful? So what we're doing is, so if x plus h is this right here, oh well, I'll just mark it again. Got a little bit messy. And f of x is right here. So we're applying the same thing. So y2 minus y1 over x2 minus x1. So if we're trying to find the slope between these 2 points, just arbitrarily, I'm going to say, okay, well, y2 is f of x plus h, and then my y1 is f of x, right? So minus f of x. And my x2 is x plus h, and my x1 is x. Well, what's x plus h minus x? Just h, right? So now what I want to do is we're going to plug everything in here, but ultimately what we're doing is we're plugging in. So if this is x squared, we need to take x plus h quantity squared minus x squared and then over h. And we want to take the limit as h approaches 0, because remember that h is the difference between these 2 points. So we're finding the slope between two infinitely close points, which is why we're going to call it its instantaneous rate of change. It's its rate of change at any given moment. So now to find its slope, we don't need 2 points. We just need one x value, and then I can plug it in and I can tell you the slope at that point. So let's see here. So if I have, let me make some room. We've derived this formula. So now let's do it with x squared. So f of x equals x squared. So I just plug in x plus h to this. So that's going to be x plus h squared, right? Minus x squared over h. So you're going to need to be real good with factoring, very comfortable with those concepts for this. So now what we're going to do is we're going to expand this right here. We're going to square this, so that's going to be x squared plus 2xh plus h squared, and then minus this x squared over h. Well, I have x squared right here and I have minus x squared, so these cancel out. So now I have 2xh plus h squared. So now, let me get rid of this. What I'm doing is I just factor out an h. So I have 2x plus h. Well, I have an h on the bottom. So these cancel, right? So now I've got a real nice and clean, very clean expression. So now I'm taking the limit as h, goes to 0 of 2x plus h. What's going to happen to this is h becomes 0. This just eliminates itself, right? So now we just have 2x. So that tells me that the derivative of x squared is 2x. Okay? So what that tells me now, how I can use that information, is I can go, okay, so let's say this is not going to be a perfect graph, but it'll get the idea across. So let's say I have x squared, and I want to know my slope at 2, okay? So the rate of change will be 2, basically I'm just plugging in 2 for x here, because this is the function of the rate of change. Any x value I plug in for this is going to tell me the rate of change of this function, x squared, at that given x value. So if I plug in 2, I get 4, right? So that means that if I drew a line, it's not going to look perfect because I just kind of sketched the graph. If I drew a line with a slope of 4, it would perfectly intersect with this line at one point and only one point. That's what a tangent line does. It only intersects at one point. A secant line will intersect at more points, like this, where it hits more than once, but that's not what we want. We only want a tangent line. So let's try a couple more examples of that. So let's say I want to find the derivative of f of x equals 2x plus 1, right? So I have to come back to this equation that we found, which again, remember, this we call this equation that I wrote a second ago the difference quotient. No. We call this the difference quotient. It's because it's the quotient of the differences between all the y values and the x values. That's why. So this is imperative. We need this for derivatives. This isn't really what we're going to use in the long run, but in math, we always want to understand why things are happening, where they're coming from, and then we employ shortcuts. But we need to know what's going on in the first place for us to really make true sense of this information later. So f of x plus h. So f of x is 2x plus 1. So I'm saying, okay, well, I want to plug in x plus h to this equation. 2 2x plus h plus 1. I suppose this, well, no, it is necessary. Plus 1 minus f of x, so 2x plus 1 over h. So now what I'm going to do is I'm going to, well, why don't I distribute this first? So I have 2x plus 2h plus 1, and then I'm going to distribute this negative, minus 2x minus 1 all over h. Oh, that's a weird h. Well, if you're doing this correctly, you're going to have terms that cancel out. It's necessary that terms get eliminated. We cannot go straight from this form to taking a limit. And here's why. Because we need to cancel this h out. Because we're taking the limit as it approaches 0. So if we leave it in exactly this form, then we're going to get something indeterminate. We're going to get a fraction with 0 in the bottom, and that doesn't give us anything. That doesn't help us. So I have 2x and I have negative 2x. So I have to get rid of this. So I have 2h minus 1 over h. So now I can do, hang on, let's see here. 2x. Let me see here. Oh, I found my mistake. I forgot to write a 1 in here. So this should be 2x plus 2h plus 1, which is what I forgot, and then minus 2h minus 1. So these ones cancel out as well. I knew I did something wrong. So now I just get 2h, right? So then these h's cancel out. So I don't even really need to take the limit anymore because I'm just left with 2. So that tells me that the derivative of 2x plus 1 is 2. So why don't we try another one? Okay, so why don't we try x cubed f of x equals x cubed. So same old thing. These can get a little bit tedious, and this will be a little bit of a tedious one. So remember, difference quotient is f of x plus h minus f of x over h. So what we would do is we would do f of x plus, oh well, hang on, let me do this differently. We're going to do x plus h cubed minus x cubed over h. So if we expand this, we're going to get, let's see here, x plus h times x squared plus 2xh plus h squared. And we need to expand that, so we're going to get x cubed plus 2x squared h plus xh squared plus hx squared plus 2xh squared plus h cubed. So we need to combine like terms. So I have just 1x cubed, x squared. So I'm going to have x squared h. So I have 3x squared h plus 1 x squared plus 2xh cubed plus h cubed. So right, so I'm going to have, once I expand all this, I'm going to have x cubed plus 3x squared h plus 3xh squared plus h cubed. So that's going to be, that's just this term expanded, right? So now I have, let me write that again, plus 3x squared h plus 3xh squared plus h cubed minus x cubed. So that's going to cancel out, right? So now I just have 3x squared h plus 3xh squared plus h cubed, and all of that is over h. So what do I do? Excuse me, I have to eliminate this h in the bottom. So I just factor out an h from the top. So I'm going to have h 3x squared plus 3xh plus h squared all over h. So these h's cancel. So now what I need to do I've gotten rid of all this. Now I'm just left with this. And actually get rid of all of this. So now what I'm doing is I'm taking the limit as h approaches 0. So what's going to happen to this function as h approaches 0? Well, 3x squared has no h in it, so it's not going to make a difference. 3xh is going to go to 0 because we're multiplying by 0. H squared is going to be 0 times 0. So all these terms cancel, and we're just left with 3x squared. So that's going to be the derivative of this function. So this is really helpful because we can do a lot of cool things with this information. Well, actually, first let me back up. There's a couple. I'm not going to go into the big tricks of it, but this is a good way to check yourself. These are derivative rules you'll learn down the road. Do not rely on them. You want to know this difference quotient backwards and front. But I can tell you a way that you can kind of check your work whenever we're dealing with exponential functions like this, or rather polynomials, stuff like that. Really all you need to do is you want to bring this exponent to the front, so this becomes 3x, and then you want to drop the degree of the exponent. So this was x cubed, it's going to become x squared. So what I did is I brought this down to the front, and then I subtracted 1 from it, and that's my new exponent. So similarly, I can do this. So x to the 5, the derivative of that. I'm going to bring down my 5 to the front, it becomes my coefficient. And then I subtract 1 from my exponent. So it's going to become 5x to the 4. Okay? So that's a really useful thing to know here. Another thing we can do, so you don't really want to rely on that yet, it's good to be able to check your work. And that's a quick way to do it. But I guarantee you any professor is going to want you to show your work, or any high school teacher, however you're taking it, anybody's going to want you to show your work, so do not rely on that. So now, getting more into the overview of derivatives, some applications, why this can be useful information. Because what if, let's say this, I have some function. So, I don't know, we'll say this is... So now, derivatives can be broken up. So if we have a fancy function like x squared plus x minus 1, or whatever that is, we don't need to consider the entire function. With the difference quotient you do, but whenever we're checking our work, or we're using the exponent rules is what we call them, we can do it each piece at a time. So we take the derivative of this first one, add it to the derivative of this, and then add it to the derivative of that, or rather subtract it. So the derivative of x squared is going to become 2x. Well, x is really x to the 1, right? So bring down your exponent and then reduce it by 1. So you have 1 times x to the 0. Well, what's anything to the 0 is 1, so it's just 1 times 1, so we just have 1. Well, negative 1 is really negative, well, I shouldn't even say that. So negative 1, how I like to think of these is we can reduce, we can think of these as separate functions, right? So I already know what my slope would be because of the derivative of x squared at any given point. X, let's think of y equals x, right? And it makes sense because that's the slope of y equals x is 1, so we get 1. Well, what's the slope of y equals negative 1? It's 0, right? There's no slope, it's a horizontal line. So it becomes negligible. The derivative of any constant is 0, okay? So now, why is this information useful? How can we put this to use? So let's say that we have the function, let's go back to something like this. F of x equals 2x squared plus 1. So that's going to be a parabola, right? So let's figure out the derivative of this. So we're going to get f of x plus h, so x plus h. I'm just plugging in x plus h, right? And then minus 2x squared plus 1. Okay, so I need to expand this polynomial, right? Well, this is all over h. So now I'm going to have 2 times x squared plus 2xh plus h squared plus 1, and then minus, I'm going to distribute my negative, 2x squared minus 1. Okay, let me go ahead and distribute this too. So 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1. 2x squared and minus 2x squared cancel, right? Negative 1 and 1, forgot to write that in there, cancel. So now I'm just left with 4x squared over 2h squared over h. So let me write that more legibly. So I'm just factoring out h right here, right? So 4x plus 2h over h. These cancel. We'll limit as h goes to 0. So what's going to happen? You're just going to be left with 4x, right? So that is the slope of this function at any given time. What can we do with that? There's a lot of things we can do with that, but this is probably the quickest and most helpful application of this concept. So let's consider this graph. So this graph is going to look something like this, right? It's going to cross at 1. So, well, this might be a little bit obvious with this function, but not with every function. So if we're looking at a parabola, actually, let me draw this bigger. I'm looking at a parabola. This can be really helpful because it can tell me where the vertex is going to be of any parabola. And it doesn't have to be a parabola. It can be any function. It can be a cubic, it can be a quartic, it can be quintic. It doesn't matter. It can tell us where the sort of the bottoms of the curves are. The vertices, but I don't know if you'd call it that for a cubic function. But just where it bends. That's what it can tell us. So let's see. So right here, our slope will be a flat line, right? Because whenever we're talking about derivatives, we're always thinking of instantaneous slopes, the slopes of a certain point, right? So we want to go, okay, when is my slope going to be a horizontal line? Well, it's always going to be at the bottom or the top of a curve, right? Of some sort of polynomial. So all I need to do is go, okay, well, this is the derivative. This is the function of the slope. When does that equal 0? Well, at x equals 0, okay? But let's say we have a little bit more complicated function. So let's say I have something like, let me do this, x cubed plus 2x minus 1. So I'm going to go ahead and save you the gory details, and I'll go ahead and tell you that it's going to be plus 2. That's going to be our derivative. So I can draw that as a graph. Well, let me do this actually. I don't want to draw the derivative. I want to draw the original function. So let's go ahead and take another function. So why don't we make it something like x cubed, plus minus 4x plus 1. So I'm not going to do all the expansion for you here because that would take a while, but this is the idea. Our derivative is going to be 3x squared minus 4. So I want to be able to just immediately tell you the points on this, some of the features of this graph. So I want to know when I'm going to have a bend in the graph, right? Because I know a cubic function, generally speaking, is going to look something like that, something in the ballpark of that. So it has more than one bend in it, right? It has one right here and one right here. So again, the whole idea here is we're going, okay, when is my slope 0? When is it a horizontal line? So all I need to do is set this equal to 0. So I'm going to get x squared equals 4/3. So x equals plus or minus 2 over the square root of 3. I'll go ahead and rationalize that. So that's going to be 2 root 3 over 3. Plus or minus 2 root 3 over 3. So let's see here what. So if you go ahead and plug that into a calculator, or I'm saying graph the function, you'll see that that's exactly true. So we're going to have something like that. So 2, let's see here. 2 root 3 over 3. So something like 1.15 and then negative that. Negative 1.15. So I'm roughly speculating here, but it seems like we're going to have something sort of to that effect. Oh no, that's not right. So what that tells me is if I graph this function out, I'm just kind of eyeballing it here, so if I have negative 1.15 is what that was, and positive 1.15, and then we know this intersects at 1. So what I'm going to have is, remember, these are not, it's easy to get confused here, these are not zeros of the function. These are not roots of the function. They're roots of the derivative. So what that means is they're bending points of the original function. So I'm going to have a bend at about right here, and then another bend at about right here. And then we're not quite sure what's going to happen after that. It's probably just going to keep going up. But, so the idea is we don't know, this will not explicitly give us the y values of that. We would have to plug this back in to find out where that's going to bend at, like what the y value is. But it will just tell us, for now, where on the x-axis that's going to happen. So I hope